Hey guys, in this lesson we're going to go through 3 induction proof exercises which all involve divisibility. Now there's an easy exercise, a medium one, and one on the higher tier. So if you want to test whether you're ready to take an assessment in induction proof, this is the way to go. Now on the first exercise, which is the easy exercise, we need to prove by mathematical induction that 5 times 7 to the n plus 1 is divisible by 6 for all positive integers. Now, given that the first thing we want to do is to write our p of n, we already have it in front of us, which is 5 times 7 to the n plus 1 is divisible by 6 for all positive integer n's. So right now, this is the propositional function, this is what we just wrote, and this is exactly what we want to prove. We want to prove that 5 times 7 to the n plus 1 is divisible by 6. We're going to test it out using the first positive integer, which is 1, to check whether we can prove the base case. And of course, as always, we'll be able to prove it. So we have 5 times 7 to the 1 plus 1, which is the same as 35 plus 1, 36, which is equal to 6 times 6. And I wrote it like this to make it clear that 36 is divisible by 6, which of course it is. But just to make it clear that us writing it, being able to write it as 6 times something, which in this case is 6 times 6, shows that we have a multiple of 6, which shows also that 36 is divisible by 6. So we write which is divisible by 6. Therefore, the base case holds. Number 3, the inductive hypothesis. We are going to assume that 5 times 7 to the k plus 1 is divisible by 6, therefore it can be written as 6 times a being a positive integer as well. And we're going to save this equation for later. We're going to assume that this is true, and we're going to substitute it into p of k plus 1 later. So now on to p of k plus 1, which is the inductive step. We're going to replace our k by k plus 1, and by using this equation right here, which I just colored green, you are going to substitute either 5 times 7 to the k by 6a minus 1 whenever it shows up in this term right here, or another strategy that also works is to replace this one right here by 6a minus 5 times 7 to the k. Notice that we're using an equation which we know, or we are assuming, that is true. I'm going to select the substitution above, but knowing that using this substitution would also work. So let's continue. We have 5 times 7 to the k plus 1 can be rewritten as 7 to the k times 7 to the first power, which is just 7. All that plus 1, which is equal to, and now we run the substitution. We have 6a minus 1 over here. So this is 7 times 6a minus 1 plus 1, which is equal to 42a minus 7 plus 1, also known as 42a minus 6, which if you factor a 6 out, gives us 7a minus 1, which is divisible by 6, as we were expecting. So now the last thing that we should do is to write the conclusion. Given that p of 1 is true and p of k plus 1 is true, whenever p of k is true for some positive integer k, then by the PMI, principle of mathematical induction, p of n is true for all positive integer n's. Now, thinking about it, let me do this exercise also using this substitution, just to show that it also works. So instead of doing this, we are going to replace 1 by 6a minus 5 times 7 to the k. Now notice that we still have 5 times 7 to the k times 7 plus 6a minus 5 times 7 to the k. And 5 times 7 to the k is a common factor for these two terms. So we have over here 5 times 7 to the k, 7 minus 1, plus 6a, which is the same as 6 times 5 times 7 to the k, plus 6a, which is equal to 6 times 5 times 7 to the k plus a, which is also divisible by 6. So we just proved it using a different substitution. It also works. So on to exercise number 2, the medium level one. Prove by mathematical induction that 7 to the n times 3n plus 1 minus 1 is divisible by 9 for all positive integers. Now we're going to start with the propositional function, as always. And writing our p of n is basically stating that 7 to the n times 3n plus 1 minus 1 is divisible by 9. So nothing new. Now, given that we're talking about positive integers, the base case is p of 1, meaning we substitute 1 into n. And let's check if this is actually divisible by 9, which of course it is going to be. So we have 7 times 4 minus 1, 28 minus 1, 27, which is 9 times 3, which means that 27 is a multiple of 9, therefore 27 is divisible by 9. So the base case holds. Now on to p of k. In the inductive hypothesis, we're going to state that 7 to the k times 3k plus 1 minus 1 can be written as 9 times a being a positive integer. And we're also going to write that we're assuming that this is true for some positive integer k. Now, for the same reason that we saw over here, writing this as 9 times a being an integer, shows us that we're getting, as a result, a multiple of 9, which is representative of a number which is divisible by 9 as well. And remember that this is the equation that we're going to use in order to substitute something into p of k plus 1 to show that we get, in p of k plus 1, a number which is divisible by 9. Now, on to p of k plus 1. Let's rewrite our p of k, substituting k plus 1 over here and over here. And this is what we get. Now, one substitution that we can use is replacing the negative 1 that shows up over here by 9a minus 7 to the k, 3k plus 1. Which means that we get 7 to the k plus 1, 3k plus 1 plus 1. And careful over here, you already took care of the negative sign over here, therefore you can just write plus 9a minus 7 to the k, 3k plus 1, which gives us 7 to the k plus 1 times 3 times k plus 1 plus 7 to the k plus 1, and our terms in blue. Notice that we can rewrite 7 to the k plus 1 as 7 times 7 to the k, giving us 21, 7 to the k plus 1 plus, again, 7 times 7 to the k plus 9a minus 7 to the k, 3k plus 1. Now, all of these, they're common to every term. Therefore, we can factor it out. So what do we get? 21k plus 21 plus 7 minus 3k plus 1, meaning minus 3k minus 1. And we also have this plus 9a outside. Now, by simplifying this, we get 18k plus 27, which can also be rewritten as 9 times 2k plus 3, giving us the following result, which of course is not the end result. We still need to factor out a 9. So we have 9 times 7 to the k, 2k plus 3 plus a. And that's it. We just need to write the conclusion now, given that we already got a number which is a multiple of 9 or divisible by 9. So which is divisible by 9. Now the conclusion is, you can just use the same one from the last exercise, the previous exercise, given that nothing changed. That's why I mentioned that at this point you're pretty much just vomiting the conclusion because it doesn't change much. And in this case, it didn't change at all compared to the previous exercise. Now on to exercise 3, the hard one. Alright, so in this hard exercise, we have to prove by induction that n cubed plus 3n squared plus 2n is divisible by 6. Now, let's see why this exercise is a bit trickier. But do know that the first 3 steps, they're always the same. It doesn't change much. It's not the first 3 steps that are going to be tricky, or it's the 4th one. So let's score these easy marks. P of n. So P of n is stating that we're trying to prove that n cubed plus 3n squared plus 2n is divisible by 6 for all positive integers. And given that we're talking about positive integers, the base case is p of 1. When n is equal to 1, we have 1 cubed plus 3 times 1 squared plus 2 times 1, which is equal to 6, which can be written as 6 times 1. So we know, of course, that this is divisible by 6. So you can also state that the base case holds. On P of k, we are substituting n by k and assuming that this is a multiple of 6, which means that it's divisible by 6. Capital A being a positive integer. So we're going to assume that it is true for some positive integer k. Now on P of k plus 1, we are going to replace k by k plus 1. So 3k plus 1 squared plus 2k plus 1. And we're going to use this equation to make a substitution into P of k plus 1. Now, one substitution that we can make is rewriting k cubed as 6a minus 3k squared minus 2k. But first, let's expand this thing. We have k cubed plus 3k squared plus 3k plus 1, which takes care of this term, plus 3k squared plus 6k plus 3, which takes care of this other term, plus 2k plus 2, which is going to make it possible for us to simplify a few terms, such as 3k squared, 2k, and this is 9k. And we also have a 4 here, which gives us 6a plus 3k squared plus 9k plus 4 plus 2, which is plus 6. And for these two terms, we can factor out a 6. So we have 6 times a plus 1, which is good. So for this one, we have a multiple of 6. However, for these two, we can only factor out a 3k, getting k plus 3 inside this set of parentheses. Now, this is the part that the exercise gets a bit trickier because we have a 6 here and we don't have a 6 here. If we only had a 2, somewhere over here, a product between 2 and 3 would give us a 6, and then we would be fine, right? But it's not the case. Now, how can we deal with that? We have two possibilities for k. Let's say that k is even, which means that this guy is even. It can be written, for example, as 2w, right? Giving us over here a 6 times w, which means that we're going to have 6 times a plus 1 plus w k plus 3, and then we're fine. We do have a multiple of 6 in this case. Now let's think about another scenario. Let's say that k is odd. If k is odd, it can be written as, for example, 2w plus 1, which means that we're going to have over here a 2w plus 1, which does not help, not right now. However, any odd number plus 3 gives us an even number, so this guy will be even. And over here, we're going to get 2w plus 1 plus 3, which is 2w plus 4. Therefore, we can factor out a 2, and we have w plus 2 over here. Therefore, we're going to have 6 times a plus 1 plus a product between 2w plus 1 and the w plus 2 that we have left over here, which means that in both cases we can factor out a 6. So in both cases we're fine. Now I know showing this can be tricky, and that's the point of the exercise, right? This is a harder type of induction proof which involves divisibility. Now, given that the conclusion is pretty much the same, it is actually the same, I'll leave you with this.